Well, here we are again, everybody, ready to talk some calculus. Today we're going to talk about derivatives of logarithms and exponential functions. So we're going to take a quick look here at e to the x, and we're going to see, based on the definition of a derivative, which is that thing that involves that limit as h approaches 0. Based on that definition, where does the derivative of e to the x come from? So let's explore that here, and then I'll show you some formulas. And again, as always with these, I like to show you where they come from. What you're responsible for is knowing the formulas so that you can use them and apply them on your AP exam. So let's take a look. So the limit as h approaches 0 of f of x plus h minus f of x all over h, when applied to e to the x, would look like this. The limit as h approaches 0 of e to the x plus h minus e to the x all over h. Now, this isn't very helpful, so I need to algebra my way through this. And I'm going to rewrite this, and I want you to see if you can tell where it comes from. The limit as h approaches 0. I'm going to take this e to the x plus h and write it like e to the x times e to the h. See if you can think about where that comes from. And if you're not quite sure, let's review. Whenever I have two like bases, like x squared times x cubed, we add the exponents. We get x to the fifth. So doesn't it make sense that if you have something like x to the a plus b, doesn't it make sense that we could write it like x to the a times x to the b? Well, that's just what I did here with e to the x plus h. E to the x times e to the h. So it should hopefully make sense. And now what I'm going to do is I'm going to algebraically manipulate this, and I'm going to factor out that e to the x. And it's going to look like this. Now, I'm also going to pull the e to the x out, because I'm evaluating the limit as h approaches 0 of this expression. And I can't do anything with the e to the x. There's no h in it, so it's not impacted in any way, shape, or form. So remember, I'm finding a derivative equation. So anything with just x in it, I'm going to be pulling out. So now I've got this function here, this e to the h minus 1, and there's really no good way to evaluate this, because no matter what I do, I get 0 over 0. If I try to split it up and do e to the h over h minus 1 over h, I actually get infinity over infinity, or minus infinity, which is another indeterminate form. And that's another video for another day, where I'm going to kind of walk you through all the indeterminate forms so we can see what those are and where they come from. But just know, infinity minus infinity, anything involving more than one infinity, with the exception of multiplication, is going to be an indeterminate form. And the reason is because not all infinities are created equal. And I guess infinity plus infinity would lead to a limit of infinity, because, you know, when you're adding two really large numbers together, it's going to be infinity. But this, the difference or the division, the quotient of two infinities, because they might be growing at different rates and approaching infinity faster or slower, there's really, you can't tell, right? So it's deceiving. So we can't do anything with this other than, at this point in time, looking at the graph. And when you look at the graph of e to the h minus 1 over h, you're going to see that as h approaches 0, this entire value actually goes to 1. So the limit there is just 1, meaning that when you do the derivative of e to the x, you simply get e to the x. So that's what's really cool about this derivative. The derivative of e to the x is just itself. Now, be careful, because there might be some chain rule issues coming into effect, where if you have an exponent of other than just x, you're going to have to consider that exponent as, you know, that u function, and you're going to have to do the chain rule. So let's go ahead and dive in and see a couple of formulas. These are the formulas for the exponential functions. And so here we've got e to the x, and remember, du dx just means chain rule for that exponent. And then this is actually the derivative for any base. So like, if I want to take the derivative of 2 to the x power, this is the formula I would use. And really, all you need to do is memorize this formula here on the right, because really, let's think about it. If e is your base, if I do e to the u, well then it's e to the u times the natural log of e times du dx. Well, natural log of e is just 1, so really this formula works no matter what. So I want you to understand that it's not two separate formulas. It's just that e to the u is so common that we write it down as its own thing. So let's practice a little bit. Here we have e to the 2x cubed. So the first thing I'm going to do is I'm going to identify what u is, e to the u, right? So u is 2x cubed, which means du dx is 6x squared. So to find y prime, it's just e to the 2x cubed. Remember, it doesn't change. It's still just e to the u. That's part of the formula. But then I'm going to multiply it by 6x squared. And when I clean it up a little bit, I'm going to wrap this up in parentheses. And I'm going to do the same thing with the exponent. That way, if I'm a sloppy writer, and I like to think that I write fairly neatly most of the time, but if I'm a sloppy writer, like I know so many of you are, it's very possible that you could be writing and sloppily, going like e to the 2x cubed 6x squared. And the AP reader who's trying to read your paper isn't going to know, is this separate or is that part of your exponent? So don't fall into that trap. Just wrap stuff up nice and neat with parentheses so it's very clear what's in the exponent and what's not. So let's try this one. Number 2, y equals 2 to the x minus 3. Well, this is one of those exponential functions. And we know the minus 3 is going to have a derivative of 0. So when I do y prime, I'm really only worried about the 2 to the x. So the function says that when I do the derivative, it's just 2 to the x times the natural log of the base, which is 2, times du dx. Well, u is x. Whenever u is just x, there's no du dx, so we don't need to worry about that. And again, I'm going to rewrite this. I'm going to wrap up that natural log of 2 and then 2 to the x power. You could wrap it up on the end. It doesn't matter what order you write it in, but parentheses are always a good thing when we're trying to separate things out. Number 3, let's take a look at this one. Well, this one's funky, but I see that I have an e to the x there. So sometimes simplifying and factoring is going to make it a little easier to work this out. And truthfully, I want to factor out the e to the x because now notice you have two product rules here that you'd have to use. I'd have to do the product rule here and then again for the second term. By factoring out e to the x, now I've created product of just two things instead of two separate product rules. So I factor out that e to the x, make it a little easier. Now I'm going to use my product rule. So this is u and this is v, which means u prime is just e to the x. V prime is going to be 2x minus 1. So now let's use our product rule. Remember, it's u v prime plus v u prime. So that's what we're going to be using. So u is e to the x, y prime equals. And then v prime is 2x minus 1 plus v, well that's x squared minus x, times u prime, well that's e to the x. Ta-da! And if I simplify this a little bit, I'm going to factor out again an e to the x because this would not appear in a multiple choice as an option. I want to make sure that I'm comfortable doing all kinds of simplification. So let me show you what I think you would see on a multiple choice problem. I think that they would want you to factor out this e to the x. So notice you have two terms here. Terms are separated by addition and subtraction. And yes, you have terms within the terms, but you have two big terms here. So e to the x comes out of everything. And what's left is 2x minus 1 plus x squared minus x. And when I combine all of those like terms in there, I have e to the x, and then, whoops, come back, x squared plus x, 2x and negative x, and then minus 1. So this, or quite possibly they may end up, it's possible that they could distribute the e to the x throughout, and that could be very reasonable to expect. But I think this is a pretty fair thing that would show up on a multiple choice test as an option for the answer to this type of problem. Okay, let's keep going. Let's take a look. We've got y equals 3 to the cotangent of x. So u is the cotangent of x. So I need to remember how to do the derivative of that, right? So du dx, whew. Okay, well, this is that pst problem, right? And so I need to think about the co-functions. Whoops. CCC. And then we're going to have a negative on the inside when we do our 3 C's. Well, the derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. So negative cosecant squared x is my derivative. So I need to remember what those are. So here we go. I'm ready to write this derivative. Y prime is just going to be 3 to the cotangent of x, so the original function, times the natural log of the base, natural log of 3, times du dx, negative cosecant squared x. And you know what, you guys, for this one I'm just going to wrap each thing up with a parenthesis and call it a day. There's really no conventional way to organize this. You can reorganize them in any order that you want. If it was multiple choice, I would hope that you could recognize it. There's not much else you can do with this one, so I think I'm going to circle it and move on. So now that we've done a bunch of exponential functions, let's look at the inverses. Let's look at logarithms and see what those look like. So when I do the derivative of a logarithm, the derivative of natural log of u is 1 over u. And there's another video that I've made where I prove what that natural log derivative is. So you can catch that later. But for now, let's apply these derivatives. So it says the derivative of natural log of u is just 1 over u times du dx. So there's my chain rule. Now, if I have the log of any base, it's 1 over u times the natural log of the base. Now, remember, natural log of x, I don't know why people struggle with this so much. It's just another way to write log base e of x, right? So if you're doing log base e of x, well then, or I guess we'll keep it as u, the derivative would be 1 over u times the natural log of the base, which is e, times du dx. Well, natural log of e is 1. So 1 over u du dx. Well, that's over here on the left. So again, in the same way, we don't need a separate formula for e to the x. We don't need a separate formula for natural log. The thing is, it's just so common that it shows up so often that we need to be familiar with it. So that's why it gets its own space. So let's go ahead and find the derivative here of this first example. So I'm going to identify what u is. U equals 2x plus 2, which means du dx is just 2. So here we go. I'm going to plug it in. The derivative says it's 1 over u, so y prime equals 1 over 2x plus 2 times du dx times 2. So now I'm going to simplify. And check this out. In the bottom, I can factor out a 2. So I'm allowed to cancel some things here. Remember, you can only cancel if you can factor it out. We can factor it out of the bottom, so we can cancel it. So our true answer here is 1 over x plus 1. That would be what I would see in a multiple choice test as an option for this problem. So let's keep going. Let's find this derivative. Log base 5 of x to the 1, or x, square root of x. Now the first thing I'm going to do is rewrite this as log base 5 of x to the 1/2 power. And so that's going to help me identify what u is and find du dx. Here, u is x to the 1/2, so du dx is 1/2 x to the negative 1/2. So now I'm ready to use my logarithm formula and find my derivative. So y prime equals 1 over, so it's 1 over u, so x to the 1/2, times the natural log of the base, natural log of 5, times du dx. Whew, that was a lot. So let's clean it up a little bit. 1 over, and I'm going to rewrite this as the square root of x times natural log of 5. And then this 1/2, I'm going to put the 2 in the bottom. And then x to the negative 1/2. Well, if I rewrite this, it becomes 1 over 2 square root of x. So technically, I have another square root of x, whoops, in the bottom. So let's go ahead and clean this up. We have 1 over 2 natural log of 5, and then square root of x times square root of x. Well, it's just going to be x in this case. Technically, it's the square root of x being squared. So really, we need to be careful about that anytime we square root and all that good stuff. But here it's just going to be just x. And it doesn't really matter because it doesn't. And then let me reorganize it. We'll say 2x times the natural log of 5. Now the reason it doesn't matter here is because really and truly x is what it is. You can plug whatever you want in for x, but according to the square root of x, you'd have to only be using positive values or non-negative values. So it really doesn't matter that much here. It's not like we have to consider anything. It's not like we get the absolute value of x. They're positive anyway, so we don't need to really think too hard on that. And again, this is not the sort of thing that shows up on an AP exam regularly or anything like that. So there we go. So I hope this has been a helpful little video to kind of walk you through some of the natural log and logarithm and e to the x and exponential functions and finding those derivatives. Remember, the toughest part about these is using your chain rule and remembering to apply that to the stuff that's inside. So we said chain rule applies when we have e to the stuff, or stuff as a power, or stuff to a power, or the natural log of stuff, or the log of stuff. So pay attention to that chain rule, because it will creep in and you'll be so ready to do the derivative of natural log that you'll forget that you need to do the chain rule. So don't get caught up on that, and don't forget, always be thinking, should I be using the chain rule here? Because 9 times out of 10, the answer is yes. So I hope this has been helpful. Remember, mastery is not expected the first time around. Practice makes proficient, and you're still going to make mistakes. You're still going to feel challenged. You're going to be stretched, and that's great. That's a good thing. This is a time for you to grow. So keep at it. You can do this. You've got this.